the distance of closest approach to the nucleus of a 7.7 mega electron volt alpha particle, right? Before it comes momentarily to rest and reverses its direction. So we have to find out the distance of closest approach, right, Manu? So
Yes,
we
sir.
know that yeah, we know that what happens in the distance of closest approach. What happens? So let's say in the distance of closest approach, we provide some energy to this alpha particle, right? And then this alpha particle goes towards the nucleus, right? Of now Aisha has it. Yeah. So this this alpha particle comes, right? And then it reaches some point and then it stops and then reverse back, right? So this is what happens in the distance of closest approach. So then this distance is called the distance of closest approach, right? That we studied. So what happens? All the kinetic energy of this alpha particle that changes to what? That changes in what? Yeah, Aisha, we are just doing some problem, and then yeah, then we will go to the topic that we will finish. Let us discuss this first. Yeah, so what happens to the kinetic energy? What happens to the kinetic energy of this alpha particle? So this
Become zero.
kinetic it becomes equal to it becomes zero, right? And all of the kinetic energy is stored in the form of potential energy, right?
Hmm.
So this becomes what? This becomes the potential energy of this atom,
Atom.
right? So this is what happens. Now we know that what is this thing which is given. So this was mega electron volt. Yeah, what I told you guys earlier. So what have I told you guys earlier? That this is the unit of energy, right? So this
Yes, sir.
mega electron volt is the energy of the alpha particle that it was projected with, right? So this
Yes, sir.
energy is kinetic energy of the alpha particle. And this is 7.7 MeV that they have provided. This is kinetic energy, right? And
Yes.
we know that what is the potential energy? Potential energy is 1 by 4 pi epsilon naught. Q1 is E, and this
Two.
has, yeah, and this has Z number of protons, so it has Ze charge, right? Where Z is the atomic number.
Sir, divided by half mv square, right?
Yeah, yeah. No, no. So divided by potential energy we are writing. So R, right? Yeah, we are writing the potential energy. This part, half mv square, this is all there. So in this question, look carefully that they have not mentioned the velocity, right? They have directly given the kinetic energy. So no need to write half mv square, right? They have given the value of half m alpha v square. They have already given, right? Which is 7.7 mega electron, right? So now we have to find this R, right? So we know that this kinetic energy is 7.7 mega electron volt, and we have to convert it in joules, right? Because SI unit is joule. So we'll convert it in a This is 2 e square z and 1 by 4 pi epsilon. How much is this value from electric charges? How much is this value?
9 into 20.
9 into 10 to the power 9, right? This is in SI loop. So this is the value. So we'll put this value 9 into 10 to the power 9 and then R naught. Okay, right. So then we can calculate R naught as 2. E is how much? 1.6 into 10 to the power minus 19. 1.6 into 10 to the power minus 19. Then we have 9 into 10 to the power 9. And then 7.7 mega electron volt. So mega is 10 to the power 6. Electron volt is 1.6 into 10 to the power minus 19 joules. So this part will cancel. And now, and yeah, so then we cannot, yeah, there's also this Z also. So in Geiger-Marsden experiment, what was this atom? What was this atom? So on what atom they experimented?
Hydrogen.
Hydrogen. In hydrogen atom they did this experiment.
Helium,
What was
helium.
helium? Helium is the alpha particle. What atom? What goes? So there was this important thing, right? That they strike. So they strike this alpha particle onto something. What was that? Gold foil, right? This was gold foil, right? So this is the atom of right. So what is the atomic number, right? Atomic number of gold is 79. This is given, right? This is given in the CRT textbook. So atomic number of gold is 79. So we can put this. And why did we use this gold? Because in Geiger-Marsden experiment, they have used this gold to observe this phenomenon, right? So then we know the value of Z also. So that is 1.6, 10 to the power minus 19 and 9. So that would become how much? So that would be 10 to the power, this is minus 10, right? Into 79 divided by 7.7 and 10 to the power 6. So how much is this thing? This is 3.2 into 79 divided by 7.7, and this goes in the upstairs. So this is minus 60, right? Okay, now I have to use the calculator. So this, so 3.2 into 79 divided by 7.7. This is 32.83 into 10 to the power minus 16 meters. So I can change this in 10, 3.8 into 10 to the power minus 15 meters. And there's a peculiar name for this order of magnitude. What do we call this order? Do you guys remember? What do we call this thing? Yeah, what this is called? So this is called femto, right? And in this case, this is called 10 to the power minus 15 meter. This is called Fermi, right? So this is called Fermi. So this is 10 to the power 3.28 Fermi. So this would be the distance of closest approach. This question. Yeah, if they would have given the velocity, then we can use this half mv square in place of this. But they have directly given this value. So this was the energy that they provided to the alpha particle, right? Yeah, is this question clear, guys? Is this clear?
Yes.
Okay, you guys, please note it down, and then we will quickly understand about the drawbacks of this Rutherford model, and then we'll study about this course. Right. Yeah, whenever you guys have written down this thing, that- and always remember these small things, right? What happens in the case of distance of two systems, right? Whenever you guys have noted it down, please tell me and join.
Done, sir.
Arshad, Assalamu alaikum, Arsalan bhai. Okay, yes, noted everyone. What about you, Aisha and Salam?
Yes, sir, I'm done.
Good. Now let us understand about the drawbacks. As I was talking about in the previous class, that there are many drawbacks of. Oh, I guess Mir has also joined. Yeah, Mir has also joined. Okay, so we didn't go ahead, Mir, and we only did this questions. Yeah, what you can do is that please take a screenshot of this question, Mir, and then go ahead. Please take the screenshot of this question. And this was on the basis of this distance of closest approach. That is the thing that we calculated, that we studied in the earlier class. Yeah. Me, did you take the screenshot?
Yes, sir.
Let us go ahead and study quickly about this drawbacks of Brotherhood model of so what was the first major drawback was the stability of it. Stability of it. So what? How does this? Yeah. So how does this invalidate the stability of atom? So as we discussed before that in classical mechanics, right? We'll talk about classical mechanics and quantum mechanics later. But in the electromagnetic theory, right? In electromagnetic theory, we have studied that whenever whenever charge particle accelerates, whenever charge particle accelerates, so it creates an electromagnetic wave. An electromagnetic wave carries some energy, right? So in this, let's say this is the nucleus, and the electrons are revolving around this nucleus with some acceleration. So from the electromagnetic theory, we know that this will create some electromagnetic waves, right? And some energy would be lost in creating this electromagnetic wave. So its energy will decrease, then its cycle would be smaller. Again, its cycle or its rotation would be smaller, 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 and then ultimately it will drop down or it will fall on this nucleus, right? But in every atom, we know now that all the atoms are stable, right? And all the electrons revolve around the in particular orbits that we already know, right? So this invalidates. So this is contradicting that we can't get a stability of atom from this Rutherford model of atom. So this was one drawback, right? So let me write this thing that if the electron revolves around the nucleus with some acceleration. So from electromagnetic theory, we know, and I will write classical here, right? Classical electromagnetic theory, we know that charge particle, in our case, this is electron, will create some electromagnetic waves and hence some energy will be lost, right? This process will continue until until all of uh, all of the kinetic energy of electron is lost and the electron falls on the which is absurd, which is absurd because we see all the elements they are stable. We see all the humans, all everything in nature is perfectly stable, right? So, which is absurd and contradicts the stability of. So this was the first drawback, and it can also right. So this was the first drawback. The second drawback is that it was experimentally observed that every element has their unique line spectrum, which was not continuous. This cannot be. explained by Rutherford. So these are the drawbacks, main drawbacks that we discarded this model, right? So when Niels Bohr was doing his experiment, so he was totally against the idea of this Rutherford model of atoms. So he was he firmly believed that this Rutherford model is the absolute one. So there is no error in the Rutherford model. But yeah, somehow he was convinced that yeah, there is some error in the Rutherford. Then he gave this idea of uh, his model of it. So we'll study about that. But you guys please note it down. And then we'll talk about the Niels Bohr model of it. The major difference, what was the major difference? Was the major difference in Niels Bohr? Yeah, whenever you guys have noted it down, please tell.
Done, sir.
Yeah, everyone noted.
Yes, sir. Done.
Yeah, only you are saying that's I guess. Yeah, Aisha, Archana, me, what about you guys?
No, sir, one minute.
Okay, yeah, please. See, Mariam, so Aisha was still noting it down. Yeah, whenever you guys have please. Arsalan, where are you?
Yes, sir, I'm doing. Yes, sir, minus one.
Yeah,
Number.
yeah, okay. And he never replied, so I guess we assume that we have how small it is. So, towards the idea or approach, and I should like to and okay, so in the classical picture, right? So, what is a classical picture, or what is classical mechanics, and what is quantum mechanics? So, in general case, whatever object we see, in our case, the object size is different, right? And that is the objects are big, right? In the meters, centimeter, in all these ranges. So, object size we can predict its position, and we can also predict its velocity. So all these two things are known to us, right? Whenever both these things are known to us, so that would be called the classical mechanics. Whenever we can measure the velocity and whenever we can measure the position both together, then it is called the classical picture or classical mechanics. But what is the size of an atom? What is the size? Yeah, what is the size of an atom? It is very small, right, in angstrom. So we cannot measure the position and size at say at the same time, right? So then we require this quantum mechanics, right? But in here, in Bohr's approach, he used this semi-classical approach, but still it comes under this quantum mechanics, right? So what was the Bohr's approach? So he assumed that Bohr's assumed the nature of atoms be quantum, right? So this was the uh, difference between the classical picture and the quantum. Rutherford assumed that this is classical mechanics, but Bose assumed that the atom is following the quantum mechanics, right? So in that way, he was able to justify that. Then he gave these postulates, right? So then he gave very important postulates, and the first postulate gave the principal quantum number, right? So it stated that the electrons revolve around the nucleus in a fixed stationary orbit, and this is also called a shell, in such a way that it never loses or gains the energy. Right, so it has some fixed energy level in which it revolves around the nucleus, which means that it has some fixed energy levels in which it orbits around the right. So in this way, from the classical approach, we can never justify this thing because electromagnetic theory, classical electromagnetic theory, there states that if it revolves around with some acceleration, then it will surely lose its energy. But in quantum picture, yeah, so we'll see that energy is quantized, and then we'll see that in that sense, it never lose its energy, right? So that was the first postulate, and it gave the idea of principal quantum number. So shells, those shells are represented by those shells are represented by n equal to 1 is, I should write, principal quantum number n, which goes from 1 to 3 amperes. So this is the first postulate. The second postulate is that the second postulate is the second postulate states that the angular momentum of the electrons revolving around the nucleus is also fixed, and it is quantized. It is the integral multiple of h by 2 pi, right? Where h is the Planck's constant. So the angular momentum of a shell, right? Let's say we have this nucleus, right? And I will write now because neutron is also discovered, so I will write neutron plus proton. And let's say the electron is revolving. So the angular momentum of this electron, right? Let's say this distance is Rn, right? This is the radius of this electron, and the velocity with which this nth electron is moving is Vn. So then this angular momentum would be integral multiple of h by 2 pi. And this h by 2 pi is also sometimes represented by h cut. So if you see this thing, then don't get confused, but this is also represented by some. Yeah. This is nh by 2 pi. And from the rotational mechanics, do you guys remember what is the angular momentum? If this is Rn, right, this is Rn, the perpendicular distance is Vn. So what is the angular momentum? Yes, do you guys remember from your rotational class, 11th class, what is the angular momentum? Angular got disconnected. Mariam, yeah, I guess. Okay, what is the angular momentum? Angular momentum is the moment of momentum, right, guys? That is defined by mass of electron n r n, and this is nh by 2 pi. So this is quantized. Here h is the Planck's constant, right? M is mass of electron, and v is the linear velocity. Velocity of nth orbit. Rn is the radius of nth orbit. So you guys please note down these things, and then we will so I should write quantum mechanics. Okay, so you guys please note it down, and if you guys have any questions, please note it down. Yeah, whenever you guys have noted it down, please tell me. I guess Mariam got disconnected, right? Yeah. So please quickly note it down, then we'll talk about the third postulate. So he gave three postulates, right? Yes, guys, noted.
Yes, sir, done.
Done. Aisha, what about you? What you guys done?
Yes, sir,
Okay.
done.
Okay. Yeah, third postulate that he gave was about the what we should do to change the orbit of the electrons, right? We know that the electrons are in the fixed orbit, right? Then how can we change the orbit of the electron, right? So let's say if electrons are in one energy level, so you want to change the energy level of those electrons, right? So let's say if you have this higher energy level and this lower energy level, right? So this is lower energy level. This is higher energy, right? So let's say at here the energy is E2 and at here energy is I guess. Yeah, hello, Vayev. I guess your network is fluctuating, right? So you please quickly take the screenshot, right, Vayev? We just understood about these things, right? So we just understood about these two postulates of. Please take the screenshot and then we talk about the third postulate.
Yes, sir.
Yeah. Whenever you have taken the screenshot, please. Then, Maria.
Yes, sir. Done.
Okay, so the third postulate states that let's say you have this higher energy level and then you have this lower energy level. So let's say if electron wants to jump from this level to this level, right? So from higher to lower, it is then what will happen? Then it will have to lose some energy, and that energy would be lost in the form of electromagnetic wave, whose energy would be h. So this much amount of energy would be released, right? And this would be the frequency of the radiated energy, right? Energy. So come from the higher energy level to lower energy level, this will release some energy, but let's say you want to increase or you want to jump this electron to the higher energy level, then it will have to gain some energy. So you'll have to provide some energy to that. So for that case, if electron wants to jump from this lower energy level to the higher energy level, then you provide this much amount of energy, right? So the change in energy, right? So it stated, the third postulate stated that the electron has to, or the electrons have to some energy and while going from higher energy level to lower energy. And the radiated or the emitted energy will have the frequency mu, whereas wavelength be that. Similarly, if the electron wants to from lower energy level higher energy level, then h new amount of energy be provided that energy. Right, so it states that electron is going right. So electron is in this state, in E2 state, and now if it releases this much amount of energy, then it will go to the lower energy level. So if we write it properly, this thing comes in this side and this goes in the other side. So this is called the change in energy, and this would be H nu, and we can also write it as Hc by lambda. So this is the third postulate. And all these postulates combined explains all the other phenomena. They explain line spectrum of hydrogen, like elements and all the other things. And yeah, and we can also get the fixed energy. These were the advantages of this model of atom. So please note it down. And then we will calculate everything. So then we'll calculate Bohr's radius, then we'll calculate velocity, we'll calculate time period, we'll calculate energy, and yeah, so all these things we'll calculate. You guys quickly just have to remember three postulates. One about stationary orbits, other about the momentum, the third one about the changing. Yeah, whenever you guys have noted it down.
Yes, sir, done.
Yeah. Maria, Maisha, any what about you guys did? Yes, okay, guys.
Mhm.
Yeah. Okay, so then let us understand, let us find out every physical parameters, right? attributes of hydrogen-like, right? And this was the drawback of this. Yeah, this was the drawback of this Bohr's model that it can only explain the hydrogen-like elements. So we can only explain hydrogen-like elements from Bohr's model, right? We cannot explain helium. We cannot explain lithium, beryllium, boron, carbon, nitrogen, every other element. We can only explain the hydrogen-like elements, right? Hydrogen-like elements from model. So what are hydrogen-like elements? One is this hydrogen, obviously. The other one is helium, and we take out one electron. Similarly, we have lithium, we take out two electrons. Similarly, we have this beryllium, we take out three electrons, and it. So these kind of elements are hydrogen-like elements, right? What is hydrogen? One, we have this nucleus, and one electron is revolving that. So that kind of element would be called hydrogen-like elements, right? So we have, let's say, a nucleus. So charge is Ze, right? This is the nucleus, and then this electron is revolving around. So first we have to find out the radius, and specifically Boole's radius. So how much is this? This radius is Boole's radius, and velocity we know that is v. So we know that this is moving in circular orbits. So if it is moving in circular orbits, then it will experience some why if it is moving in circular orbits, then at towards the center it will experience some force. What kind of force is that? Yes, if it is moving in circular orbits, so whenever something is moving in circular orbits, so
Centripetal force.
centripetal force, right? Absolutely right. So we have this centripetal force, which is m mass of the electron Vn square by r. Right. This is the centripetal force. Now, what is providing that centripetal force? We have this. We have this positive particle, and we have this negative electron, negative charge particle. So, what is providing that centripetal force? What force is attracting this electron towards its side? What force is attracting? Yeah, what force is attracting this electron towards its center? Yeah, please.
Attractive.
Yeah, Coulomb force, right? Electromagnetic force, electrostatic force, right? So then this is attracted by this Coulomb force, right? Both are, let me write it as same, and this is right. So how much would be the Coulomb force? That would be 1 by 4 pi epsilon naught, right? And the charge on electron is E, and charge on this thing is Ze divided by R square, so Rn square, right? So both these forces are balancing each other. So this centripetal force is provided by this Coulomb force. So if this is moving in circles, so then these forces would be right. F centripetal, that would be equal to F Coulomb. And I have not wrote the direction, right? Because this is minus, so this would be minus of that thing, right? I'm only talking about the magnitude. Magnitude. So if we equate this thing, right? If we equate this thing mvn square by rn, and that is equal to z e square by 4 pi epsilon rn square. So one square and one thing cancels out. So what we will have? We will have Rn that would be equal to Ze square divided by 4 pi epsilon naught and mvn square. So can you guys, now we have got this force radius, but we have one unknown still there. Z we can know, E we know. All these things we know. What is the unknown that is there in this equation? What is the unknown which is remaining? Yes, guys, what is the unknown that we have? What Aisha got? Yeah, what is the unknown that we have to replace, that we have to figure out in this part? This Vn, right? Vn we also know, right? So this Vn we have to figure it out from somewhere else. And this Vn, from where we can find out this Vn? Can you guys tell me from where we can find about this Vn velocity? Yeah, something clicking. Remember, this is Bohr's postulates. This is related to Bohr's postulate. So from where we can get this Vn? Can you guys think about it? We have to replace this Vn. We have to remove this Vn because we want to calculate this Rn, right? So how can we remove this Vn? Remember the postulates, Bohr's postulate. So which postulate we can use? Yes, guys, which postulate? Yeah, so h by 2. Yeah. So Aisha is saying angular momentum on second postulate. So can we use the second postulate? What is the second postulate from second postulate? What do we have? We have m v r, that is nh by 2 pi. This is the second postulate, right? So if we want to calculate only this Vn, so that would be how much? Vn would be Nh divided by m and pi and then r. So if we calculate Vn square, so that would be how much? That would be n square, h square, m square, 4 pi square, rn square. These are the values that we get. And we will put back this value in here. So let me write it in here. So if we put back this value, so Rn would be Z e square divided by 4 pi epsilon naught m, and Vn square is n square h square divided by m square and 4 pi square. Oh, so this was, yeah, 4 pi square and also Rn square, right? So this would be this thing. And again, one Rn will be cancelled, and this pi, this square will cancel, this 4 and this 4 will be cancelled. So Rn would be how much? Value of Rn, we get this would be m, and yeah, this will also get cancelled. So we'll get what? We will get n square, h square, epsilon naught, divided by z e square and m and pi. So these would be the values that we get. So Rn would be how much? That would be h square epsilon naught n square divided by z m e square pi. So this is the value of the nth radius. This is a very important one. And there's another form that we can use. And what is that form? So we can put the value of h, right, which is 6.626 into 10 to the power minus 34. We can put the value of epsilon naught, which is 8.85 into 10 to the power minus 12. We have this E, which is how much? 1.6 into 10 to the power minus 19. We can put M, which is 1.66 into 10 to the power minus 31. And we can also put this pi, which is 3.14. If we put all these values, then we will get this thing as Rn, that would be 0.529 and n square divided by z. So this would be, and this would be in angstrom, right? This would be in meters. This would be in angstrom. This this is called the Morse radius, and this is also called Morse. So we have to remember this also and this also. Both the things we have to remember. Is this clear, guys? Is this one clear? Yeah.
Yes, sir.
And remember, whenever, yeah, so it is directly proportional to n, and this is inversely proportional to z, right? So if atomic number increases, then this Moore radius will decrease. And if the number of shell increases, so obviously the radius will also increase, right? So, and yeah, please note down this part. This thing I have already noted down. So please note down this. Yeah, please quickly note it down, guys, and then we'll talk about velocity. We have to also talk about time period, and then we'll talk about energies. Then this chapter.
Done, sir.
Done. Everyone are noted?
Yes, sir.
Done. Yeah. So you guys can see that, right? So if you put n equals to 1, so for first shell, for first shell and for hydrogen. If let's say you are talking about hydrogen atoms, so Z would be 1. So R naught would be how much? That would be 0.529. So this is the group's 0.529 angstrom. This is called the group's radius, right? Okay, so yeah, then let us also solve this velocity. So other thing that we have to calculate is velocity of the nth orbit, right? What would be the velocity of nth orbit? So we have already solved Vn. That was how much? Vn was, let us use this thing, n square, h square, m square, 4 pi square, and Rn square. And again, this is the unknown. And we have already found out this thing. Oh, again got disconnected. So network is now Mariam got disconnected. So sometimes Arsenal is getting disconnected, then Aisha, and then Mani. Then we will put the value of this Rn, right, from here. So Rn is how much? Let me just write this thing down in here. Rn is h square epsilon naught n square, h square epsilon naught n square divided by zme square, zme square pi. So this is Rn. So if we calculate Rn square, so Rn square would be how much? That would be h4 epsilon naught square n4 and z square and m square e4 pi square. So this would be Rn square. If we put this value in here, so Pn would be how much? N square, h square, m square, 4 pi square. Rn is h4 epsilon naught square and n4 and this is z square, m square, e4 and pi square. So pi square will cancel, right? And then what do we have? So n square and this is n4. This would be 2. And then m square will cancel it, right? And then what do we have? We have n. So epsilon naught square is there, and this is x square. So what are we getting? This is Vm, and this is z square e4 divided by how much? So 4 epsilon naught square, right? And yeah, 4 epsilon naught square h square and n square, right? So this would be the Vn, and if you write it properly, so this is z square by n square, and this is e4 by 4 epsilon naught square and h square. So this is the other thing. And if we multiply it by, yeah, so if we multiply it by c, right? So then this thing, okay, so we'll stop it at here. So we can z square n square e4 by 4 epsilon naught square h square. This is the velocity of nth orbit. But we have another constant, which is yeah, C by 4 pi epsilon naught C H cut. So this is called right H cut square. This is called Sommerfeld constant. Right? Let me check this value. But you guys please note down this. So I will check this value. What is this? And this is also important. So we can write this velocity in the form of that. So please note it down. This would be the velocity of an orbit, and in the meanwhile, let me check this other constant, which is called Sommerfield's constant. Square by 5. Hey, you guys, please note it down, and meanwhile, I will check constant.
Yes, I noted down.
Oh, you already noted it down. Yeah, so they have got different values. It is where why we are getting where h sun calculation. Oh, yeah. So you see that, right? So this is Vn square that we have put the value, right? Not yeah, so Vn square that we have right. So this value we should not put. We have to write this value. Yeah, we have to put this value. Rn we know, and we have to use right. Vn is this. This is Rn square, right? This is Vn square, right? So please some corrections in there. Yes, we have to correct this. That was a Vn square, right? Vn is this thing, right? We can directly write the value. Vn square is Rn square. So we got Vn square. Whatever we have written, that is Vn square, not Vn. So Vn, yeah, please correct this thing. This is NH by pi m and Rn. And now we can put the value of Rn. Correct. This is NH pi m and Rn is how much? Rn is h square epsilon naught n square. H square epsilon naught n square and divided by z m p square pi. So this is the value. Pi cancel, and then we have this h and this h cancel, and this m cancel. Now it is. So this, yeah, whatever we got, we have to take the root, right? This is actually Pn square. Yeah. This would be how much? This Vn would be Zn e square by this n and this n also cancel. We have Z e square by pi h and epsilon naught n. Right, so this is what we get, right? Check. So this would be Vn, and if we write, if we take this thing Z by N the other side, and this is E square by 2H epsilon naught. And if we multiply it by C divided by C, so this thing, right, this ZC by N and this E square by 2HC epsilon naught. So this is called the Sommerfeld constant. This is Sommerfeld constant, and we can write this Vn as alpha ZC by this is the nth order velocity, and value of alpha is 1 by 136. This is a very important point. Now, please, yeah, please correct this thing. Write down this value. Sorry about that. With this square, please correct this thing, and whenever you guys have put it. Yeah, whenever you guys have put it down.
Yes, sir, done.
Yeah. So Aisha and Mir, what about you guys? Done. Okay, so we have calculated the radius, we have calculated this velocity, and you guys can see that this radius varies as n square. This velocity varies as 1 over n. So this is inversely proportional, right? This is inversely proportional to 1 over n. This is directly proportional to n square. And yeah, in the numerator we see z, in the denominator we see z. So these are the crucial difference between velocity and radius. Similarly, what is the total energy? Or before we calculate that, let us calculate the time of revolution. So we have this nucleus, right? And we have this electron which is revolving around. And this has Rn radius. This has Vn velocity. So this is covering, let's say, t time it is taking to revolve this thing around. So what would be the total distance? If we complete one revolution, what would be the total distance, guys? If it completes pi r, right? So total distance is 2 pi r n. Velocity or speed is Vn. So time would be how much? That would be distance by speed, right? Distance by speed. So this would be how much? This would be 2 pi r n, and this is Vn, right? So we already know that what are the values of Rn and Vn, and we can put those values. So, or we can also write n. Rn is nh upon 2 pi n. Yeah, so then Rn is square. Okay. So what we can do is that either we can put all these values of Rn and Vn, or we can use the second postulate, right? That so let us use the second postulate. Second postulate is what? Mn Rn is NH by 2 pi. So Vn is NH by pi and mRn. So if we put this value, pi Rn divided by NH and 2 pi mRn, this would be how much? This would be T would be 4 pi square and mRn square divided by NH. And now we can put the value of Rn square, right? So NH Rn is how much? Rn is h square epsilon naught n square, h square epsilon naught n square divided by, yeah, these are the calculations that we do. ZME square pi. ZME square pi and whole square. This would be how much? 4 pi square m and h4 epsilon naught square n4 divided by nh and z square m square e4 pi square. Pi square cancel. This is n and n4, so this is q. This m and m cancels, and yeah, h, and this is q. So t is how much? T is n cube epsilon naught square h cube divided by z square m e. This is the time. Okay, you guys quickly note down this time period, and then in the next class we'll talk about this. So we'll solve one question, and then it would be very easy to understand. So you guys please note down this one, right? And let me check if I did it right. N is NH by 2 pi m Rn, NH by 2 pi Rn, pi 2 pi square m Rn square. Yeah, so I guess this is correct. Quickly note it down, and then we'll stop here. And in the next class, we'll finish this chapter. We'll calculate the total energies, and then we'll do some numericals, and then we will finish this chapter and start the new chapter. Okay. Oh, there is this 4 also, right? There is this 4 also.
Yes, sir, done.
Okay, so we'll stop at here, and yeah, guys, please revise this part. This is lengthy, but it is quite easy. It's only calculation and you guys practice this part, and this comes in 5 marks question, right? So they will ask you to derive the radius, the velocities, and this time period. So this you can do, right? So just you have to revise. Guys, practice that part. And what about you, Aisha and me? Note it.
Done.
Yeah, note it.